March 13th, 1943. Seneca, Illinois. The morning frost clung to the cornfields that surrounded the most improbable shipyard in American history. Frank "Red" Sullivan pulled his collar tight against the bitter wind as he walked through the gates of the Chicago Bridge and Iron Company's Prairie shipyard. At 28, he carried himself with the confident stride of a man who had spent 15 years coaxing steel to bend to his will. His lunch pail contained not just sandwiches wrapped in wax paper, but detailed sketches of welding modifications that could get him fired. The Illinois River stretched like a muddy ribbon past the 200-acre facility, where massive steel ships rose incongruously from what had been pasture and farmland just 18 months earlier. 15 parallel construction berths stretched 3/4 of a mile along the riverbank, each one holding the skeleton of a landing ship tank in various stages of completion. The sound was overwhelming. The thunder of pneumatic hammers, the screech of steel being cut and shaped, the constant rumble of cranes moving sections weighing dozens of tons. Sullivan paused at the edge of construction berth number 12, where LST 511 sat waiting for him. 328 feet of flat-bottomed steel that would somehow need to survive Atlantic storms, then drive itself onto enemy beaches to deliver 20 Sherman tanks directly into combat. The mathematical impossibility of the task still amazed him. How do you build a ship strong enough for ocean crossings, yet light enough to float in 3 feet of water? How do you weld 1,340 tons of steel into a vessel that must be both ocean-going freighter and assault craft? Inside the hull, the tank deck stretched like a steel cavern. The air was thick with the acrid smell of welding flux, hot metal, and the sweat of men working double shifts to meet impossible deadlines. Sullivan climbed down through the access hatch, his welding equipment clanking against the steel ladder rungs. In his hands was a modified welding gun that incorporated techniques his supervisors had explicitly forbidden him from using during official work hours. The specific modification was subtle but revolutionary. Instead of the standard coated electrodes used in shielded metal arc welding, Sullivan had rigged a continuous wire feed system that deposited bare metal wire beneath a blanket of granular flux. The process was called submerged arc welding, and it had the potential to increase welding speed by factors that seemed too good to believe. But Chicago Bridge and Irons management had repeatedly ordered him to abandon these experiments. What Frank Sullivan didn't know, crouched in the belly of LST 511 with his unauthorized equipment, was that his forbidden technique would transform American shipbuilding from a desperate scramble into an industrial miracle. Within 8 weeks, his banned method would be officially adopted across all LST construction sites. Within 6 months, it would cut assembly time from 3 weeks to 72 hours. The welding process that supervisors called dangerous and unproven would help build the fleet that carried Allied forces onto the beaches of Sicily, Italy, and Normandy. The Illinois wind howled through the gaps in the hull plating, carrying with it the sound of a nation struggling to build weapons faster than enemies could destroy them. In the distance, a locomotive whistle echoed across the prairie, carrying steel from Gary, Indiana, and Pittsburgh, Pennsylvania, to be transformed into instruments of liberation. Sullivan adjusted his welding helmet and struck an arc beneath a mound of flux that would change the course of the war. The crisis that brought Frank Sullivan to a cornfield shipyard had begun 18 months earlier in the oak-panelled war rooms beneath London, where Winston Churchill studied maps that showed the stark reality of Britain's strategic position. German U-boats were sinking merchant ships faster than Allied shipyards could replace them. The traditional strategy of establishing beachheads through existing ports had proven catastrophic at Dieppe, where Canadian and British forces suffered 70% casualties attempting to capture a fortified harbour. Churchill understood that victory required a fundamental reimagining of amphibious warfare. Instead of capturing ports, Allied forces needed the capability to create their own harbours on any enemy beach. This meant developing vessels that could cross oceans, carrying the heavy equipment necessary for sustained operations, then deliver that equipment directly onto hostile shores without requiring piers, cranes, or any existing infrastructure. The technical requirements seemed to violate the basic principles of naval architecture. An ocean-going vessel required deep draft for stability in rough seas. A beaching craft required shallow draft to approach shore. The ship needed structural strength to survive Atlantic storms that could generate waves 50 feet high, yet it had to be light enough to float with only 3 feet 9 inches of water beneath its keel. Most critically, it needed to carry enough cargo to make a meaningful military impact while remaining small enough to be mass-produced by shipyards that had never built anything larger than river barges. On November 26, 1941, a small British delegation arrived at the Washington Navy Yard with blueprints that represented months of desperate experimentation. The designs showed converted oil tankers with their bows cut away and massive doors installed. 3 prototype vessels had been constructed using this method, and the results were uniformly disappointing. The conversions were slow, expensive, and structurally questionable. The British Admiralty's own engineers admitted that the design was inadequate for the massive amphibious operations that would be necessary to open a second front in Europe. The meeting that followed would reshape American industrial capacity in ways that neither nation fully understood. Representatives from the Royal Navy, the United States Navy's Bureau of Ships, and several private shipbuilding companies gathered around tables covered with blueprints, engineering specifications, and production estimates that seemed to exist in the realm of fantasy rather than achievable reality. Captain Edward Cochrane of the Bureau of Ships examined the British specifications with the methodical attention of an engineer who understood that mathematical precision would determine whether Allied forces could ever return to continental Europe. The requirements were stark and unforgiving. The vessel needed to carry at least 20 medium tanks or the equivalent weight in vehicles and supplies. It needed to cross the Atlantic independently, without requiring escort vessels for mechanical support. It needed to approach within 50 yards of any gently sloping beach, lower a ramp, and discharge its entire cargo in less than 4 hours. The British had calculated that successful operations in Europe would require at least 2,000 such vessels, with additional ships needed for simultaneous operations in the Pacific theatre. At conventional shipbuilding rates, constructing such a fleet would require 15 years. The war would be won or lost long before the first ship was completed. The American response came from an unexpected source. John C. Niedermeyer, a 34-year-old naval architect who had spent most of his career designing submarines, submitted a revolutionary proposal that would become the foundation for the most ambitious shipbuilding program in human history. Instead of converting existing vessels, Niedermeyer proposed building purpose-designed ships that could fulfill the contradictory requirements through innovative engineering rather than compromise. His design featured a flat keel that would allow the ship to be beached and remain upright, twin propellers and rudders positioned high enough to avoid damage during grounding, and an internal ballast system that would allow the same vessel to achieve both deep ocean stability and shallow water operations. Most ingeniously, the bow would incorporate massive clamshell doors that could open to reveal a ramp capable of supporting the weight of a Sherman tank. The ballast system was adapted from fleet submarine technology that Niedermeyer understood intimately. During ocean crossings, the ship would take on water for stability, riding low with a draft of 14 feet. For landing operations, pumps would empty the ballast tanks, raising the ship in the water until its draft was reduced to less than 4 feet. The transformation from deep-water vessel to shallow-draft landing craft could be accomplished in 30 minutes using equipment that was already proven reliable in submarine service. Niedermeyer's preliminary sketches, drawn in November 1941, became the design template for more than 1,000 LSTs that would be constructed over the following 4 years. The final specifications called for a vessel 328 feet in length with a 50-foot beam, capable of carrying 2,100 tons of cargo while maintaining a maximum speed of 11.5 knots. The ship would be armed with 7 40mm and 12 20mm anti-aircraft guns, sufficient to defend against air attack, but not heavy enough to engage enemy warships. The decision to approve construction before completing prototype testing reflected the desperate urgency of America's strategic position. The attack on Pearl Harbor had occurred just days before Niedermeyer submitted his design. German submarines were sinking American merchant ships within sight of the East Coast. The Soviet Union was demanding immediate action to relieve pressure on the Eastern Front. Every month of delay meant additional months before Allied forces could establish a foothold in Europe. President Roosevelt's authorization came with production targets that seemed divorced from physical reality. The Navy ordered 1,000 LSTs to be constructed within 3 years, with the first ships to be completed within 18 months. To achieve these goals, construction would need to begin at multiple shipyards simultaneously, using workers who had never built ships, techniques that had never been tested, and materials allocated through a priority system that was still being developed. The challenge of where to build the LSTs revealed both the crisis and the opportunity facing American industry. Coastal shipyards were overwhelmed with contracts for aircraft carriers, battleships, cruisers, and destroyers. The traditional centers of American shipbuilding, Newport News, Bath Iron Works, Mare Island, simply lacked the capacity to add LST construction to their existing commitments. The solution emerged from a recognition that LSTs, unlike other warships, could be built inland and transported to the ocean. Their flat bottoms and shallow draft made them ideally suited for river construction. More importantly, the heartland contained both the steel production facilities and the skilled metalworkers necessary for rapid construction. The challenge would be transforming bridge builders, tank manufacturers, and industrial fabricators into shipbuilders capable of producing ocean-going vessels. Chicago Bridge and Iron Company received their LST contract in May 1942, based primarily on their reputation for welding complex steel structures. Founded in 1889, the company had built water towers, storage tanks, and pressure vessels across America. Their welders were renowned for producing leak-proof joints in structures that contained everything from municipal water supplies to petroleum products. If anyone could master the demanding welding requirements of LST construction, it would be the craftsman who had spent decades making steel tanks that never failed. The site selected for LST construction was 200 acres of Illinois farmland along the Illinois River, 30 miles downstream from the existing Chicago Bridge and Iron facilities. The location offered several crucial advantages. Solid sandstone bedrock lay just beneath 30 inches of topsoil, providing a foundation capable of supporting the enormous weight of steel stockpiles and completed ships. The Illinois River connected to the Mississippi River system, allowing completed ships to reach the Gulf of Mexico for final fitting and delivery to combat theaters. Most importantly, the site was surrounded by the infrastructure necessary for mass production. Steel mills in Gary, Indiana, and Chicago could deliver raw materials by rail. The region contained thousands of skilled metalworkers employed in automotive, agricultural equipment, and heavy machinery manufacturing. Unlike coastal areas, where military security concerns limited the availability of workers, the Midwest offered access to a large labor pool that included both experienced craftsmen and workers who could be trained rapidly for shipbuilding tasks. Construction of the Seneca shipyard began in June 1942, while the first LST keel was being laid at Newport News Shipbuilding in Virginia. The parallel development of facilities and ships reflected the urgency that drove every aspect of the LST program. Normal shipyard construction required 3 to 5 years of careful planning and gradual expansion. The Seneca facility was designed, built, and placed in operation within 6 months, while simultaneously training workers who had never seen an ocean-going vessel. The physical transformation of Illinois farmland into a shipyard capable of producing ocean-going vessels was itself a remarkable achievement. 15 parallel building berths were constructed, each one capable of supporting the weight of a large, completed LST. Massive overhead cranes with 50-ton lifting capacity were installed to move hull sections that weighed more than most entire buildings. A rail network connected each berth to storage areas where thousands of tons of steel plates, frames, and fittings were stockpiled. The first LST keel was laid at Seneca on June 15, 1942, marked by a ceremony that drew representatives from the Navy, Chicago Bridge, and Iron's corporate headquarters, and local officials who were still struggling to comprehend the scale of the industrial transformation occurring in their community. The event was broadcast over local radio stations and covered by newspapers across Illinois as evidence that the American heartland was contributing directly to the war effort. Frank Sullivan's journey to the Prairie shipyard reflected the broader mobilization of American industrial expertise for wartime production. Born in 1914 in the Irish neighborhoods of Chicago's South Side, he had learned welding during the depths of the Great Depression, when any skill that could provide steady employment was worth pursuing. His father, Patrick Sullivan, had been a steel worker at the South Works of U.S. Steel until the plant closed in 1932, leaving the family dependent on charity and whatever work Frank could find. At 18, Frank apprenticed with Murphy Construction, a small company that specialized in structural steelwork for Chicago's building boom. He spent 5 years learning to weld the framework of skyscrapers, working hundreds of feet above the streets while Lake Michigan wind threatened to tear him from narrow steel beams. The work was dangerous and demanding, but it taught him to read steel like a book, understanding how different alloys behaved under stress, how temperature affected weld penetration, and how to produce joints that would hold for decades under extreme conditions. The skills that Sullivan developed building Chicago, skyscrapers, translated directly to the challenges of shipbuilding, but the scale and precision requirements of LST construction exceeded anything he had previously encountered. Each LST required welding 23,300 individual steel pieces, ranging from massive hull plates, weighing several tons, to delicate fittings that required tolerances measured in thousandths of an inch. The total weight of steel in each ship was 1,340 tons, roughly equivalent to the structural steel in a 20-story office building. The welding specifications for LST construction were unlike anything previously attempted in American shipbuilding. The vessels needed to survive Atlantic storms that could generate wave heights exceeding 50 feet and wind speeds over 100 miles per hour. They needed to withstand the shock of grounding on beaches at full speed, then endure the stress of being pounded by surf while unloading cargo. Most critically, they needed to maintain watertight integrity, while their ballast systems alternately flooded and emptied thousands of tons of seawater. Traditional shipbuilding had relied on riveted construction, with steel plates held together by thousands of individual rivets installed by teams of workers using hammers and pneumatic tools. Riveting was labor-intensive and time-consuming, but it had proven reliable for decades of merchant ship construction. The transition to welded construction offered significant advantages in terms of speed and structural integrity, but it required welding techniques that were largely untested in shipbuilding applications. The fundamental challenge was achieving full penetration welds on steel plates that were often 3/4 of an inch thick. Unlike the thin sheet metal used in automobile manufacturing or the structural steel used in building construction, ship plates required weld joints that were as strong as the base metal throughout their entire thickness. A partially penetrated weld might appear sound on the surface, while containing internal defects that could lead to catastrophic failure during storm conditions or combat operations. Shielded metal arc welding, the standard technique used by most American shipyards, required multiple passes to achieve full penetration on thick plates. Each pass had to be carefully cleaned and inspected before the next layer of weld metal could be applied. The process was methodical and reliable, but painfully slow when applied to the long, straight seams that characterized LST construction. A typical longitudinal seam connecting two major hull sections might require 30 hours of welding time using traditional methods. Sullivan's experience with structural steel construction had exposed him to experimental welding techniques that were being developed for industrial applications. He had read technical journals that described automatic welding processes used in pipeline construction, where long, straight joints needed to be completed rapidly with consistent quality. The process that most intrigued him was submerged arc welding, which had been developed by the National Tube Works Company for manufacturing large-diameter pipes. Submerged arc welding represented a fundamental departure from traditional welding methods. Instead of using coated electrodes that were consumed during the welding process, the technique employed bare wire that was fed continuously into the weld joint. The wire was surrounded by a blanket of granular flux that melted during welding to form a protective slag covering. Most importantly, the entire arc was hidden beneath this flux blanket, completely submerged and invisible to the welder. The advantages of submerged arc welding were substantial, but largely theoretical in shipbuilding applications. The process could deposit weld metal at rates 5 to 10 times faster than conventional methods. The hidden arc eliminated the harsh light and fumes that made traditional welding physically demanding and potentially dangerous. The consistent wire feed and flux coverage produced welds with superior metallurgical properties and fewer defects than hand-welded joints, but the disadvantages seemed equally significant. The process required specialized equipment that was expensive and largely untested in shipyard environments. The technique could only be used in flat or horizontal positions, limiting its application to certain types of joints. Most concerning to shipyard supervisors, the hidden arc made it impossible for welders to observe the weld pool directly, requiring them to judge weld quality based on indirect indicators like wire feed speed and flux consumption. Chicago Bridge and Irons Management had investigated submerged arc welding in early 1942, when it became clear that traditional welding methods would not be sufficient to meet Navy production targets. A team of engineers visited the National Tube Works facility in McKeesport, Pennsylvania, to observe the process in operation. Their report acknowledged the potential speed advantages, but raised serious concerns about quality control and the difficulty of training shipyard workers in the new technique. The decision to prohibit experimentation with submerged arc welding during production hours reflected legitimate concerns about the risks of implementing unproven technology in warship construction. Unlike commercial vessels, which could be recalled for repairs if defects were discovered, LSTs would be sent into combat where weld failures could result in the loss of ships, crews, and crucial military equipment. The Navy's acceptance criteria were stringent, with detailed inspection requirements that left no margin for error. Sullivan's initial interest in submerged arc welding was sparked by frustration with the slow pace of LST construction, rather than any theoretical understanding of metallurgical advantages. Working on the night shift, he observed that most of his time was spent positioning and repositioning equipment, cleaning weld joints between passes, and waiting for inspectors to approve completed work. The actual time spent depositing weld metal was a small fraction of the total time required to complete each joint. The specific challenge that drove Sullivan to experiment with forbidden techniques was a complex longitudinal seam that connected the port and starboard sides of LST 511's hull to the bottom plate. The joint was 80 feet long and required a weld that was 3/4 of an inch deep to achieve full penetration. Using conventional methods, the seam required 4 separate passes, with extensive cleaning and inspection between each pass. The total time for completion was typically 14 to 16 hours, during which the ship occupied valuable berth space and tied up skilled workers who could have been working on other vessels. Sullivan had calculated that if submerged arc welding could complete the same joint in a single pass, as technical literature suggested was possible, the time savings would be enormous. More importantly, the single-pass weld would eliminate the internal interfaces between multiple weld layers, potentially producing a stronger and more reliable joint than conventional multi-pass welding. The opportunity to test his theory came during the night shift on March 8, 1943, when a mechanical failure in the overhead crane system suspended work on LST 511's main assembly. Rather than remaining idle, Sullivan used the unexpected break to experiment with a makeshift submerged arc setup in a remote corner of the fabrication shop. Working with Tom Mueller, a fellow welder who had experience with automatic welding equipment from his previous job at a locomotive repair facility, Sullivan rigged a wire feeding system using components borrowed from the maintenance department. The improvised equipment was crude but functional. A discarded motor from a damaged crane provided the power to feed bare welding wire at a controlled rate. A hopper fabricated from scrap steel contained the granular flux that would submerge the arc. The welding power source was a standard unit used throughout the shipyard, but Sullivan modified the control settings to provide the constant voltage characteristics that submerged arc welding required. The first test weld was conducted on a section of scrap hull plate, identical to the material used in LST construction. Sullivan positioned the plate horizontally and established an arc beneath a mound of flux, then began feeding wire continuously while moving the entire assembly along the joint. The results were immediately impressive. The weld penetrated completely through the 3/4-inch plate in a single pass, with no visible defects or irregularities. More importantly, the deposition rate was approximately 6 times faster than conventional welding methods. Over the following week, Sullivan and Mueller refined their technique during off hours, experimenting with different wire feed speeds, travel rates, and flux compositions. They discovered that the key to success was maintaining precise control over the relationship between wire feed speed and travel speed. Too fast, and the weld would lack penetration. Too slow, and excessive weld metal would build up, creating irregularities that could weaken the joint. The breakthrough came when Sullivan realized that submerged arc welding required a fundamentally different approach to quality control than conventional methods. Instead of relying on visual observation of the weld pool, welders needed to monitor indirect indicators like the sound of the arc, the appearance of the flux layer, and the consistency of the slag formation. These skills could be developed through practice, but they represented a completely different set of techniques than those used in traditional welding. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The breakthrough that would transform American shipbuilding occurred at 3:47 in the morning on March 26, 1943. Sullivan and Mueller had been working since midnight on a particularly challenging section of LST 511's hull, a longitudinal seam that connected the port side plating to the central keel structure. The joint was complicated by the intersection of three separate hull plates, each one requiring precise alignment to ensure that the ballast system would function properly when the ship reached operational service. Chief Welding Inspector Harold Jenkins had been struggling with this joint for 3 days, using conventional welding methods. The intersection created stress concentrations that caused the steel plates to warp slightly during welding, requiring constant adjustment and re-welding to maintain proper fit. The work was progressing at a rate that would require 10 more days to complete, far behind the accelerated schedule that the Navy was demanding. Jenkins was a 42-year-old veteran of 20 years in steel construction, including 5 years as a welding supervisor for the construction of the Golden Gate Bridge. He had seen every type of welding challenge that structural steel could present, but the LST construction requirements exceeded anything in his previous experience. The combination of thick plates, complex geometry, and stringent quality requirements created problems that conventional techniques seemed unable to solve efficiently. Sullivan approached Jenkins during the shift change, carrying samples of the submerged arc welds he and Mueller had been perfecting during off hours. The test pieces showed weld penetration that was superior to anything Jenkins had seen from conventional methods, with metallurgical properties that exceeded Navy specifications. More importantly, the samples represented only 90 minutes of work to complete joints that would normally require 6 hours using traditional techniques. Jenkins examined the samples with the methodical attention of someone whose professional reputation depended on accurate assessment of weld quality. He performed visual inspections, bend tests, and cross-sectional examinations that revealed the internal structure of the welds. The results were undeniable. The submerged arc technique produced joints that were not only faster to complete, but actually superior in strength and consistency to conventional welds. The demonstration that followed became legendary in the history of American shipbuilding. Working under Jenkins' direct supervision, Sullivan used his improvised submerged arc equipment to complete the problematic intersection joint in just under 2 hours. The weld showed perfect penetration, no distortion, and mechanical properties that exceeded Navy requirements by significant margins. Most importantly, the speed of completion meant that LST 511 could return to the normal construction schedule instead of falling further behind production targets. Jenkins immediately brought the demonstration to the attention of Production Superintendent William Hayes, a former automotive engineer who had been recruited from Ford Motor Company specifically to solve LST production problems. Hayes understood that the difference between success and failure in wartime production often came down to seemingly small improvements that could be scaled across entire manufacturing systems. Hayes was under enormous pressure from Navy representatives who were threatening to transfer LST contracts to other shipyards if Seneca couldn't meet production targets. The previous month, the facility had delivered only 3 LSTs instead of the promised 6. Every day of delay meant fewer landing craft available for planned operations in Europe and the Pacific. The Navy had made it clear that LST availability was a critical constraint on Allied strategic planning. The controlled test that Hayes authorized represented a calculated risk that could either solve Seneca's production crisis or create an even worse disaster if the new welding technique failed in service. A complete longitudinal seam on LST 511 was selected for the demonstration, with Navy inspectors present to evaluate both the welding process and the quality of the completed joint. The test would either validate submerged arc welding for LST construction or confirm management's concerns about implementing unproven technology in warship manufacturing. The test began at 6 in the morning on March 29th, with representatives from Chicago Bridge and Iron's corporate headquarters, the Navy Bureau of Ships, and the Seneca shipyard management observing every detail of Sullivan's technique. The 80-foot seam being welded represented one of the most critical structural elements in the entire ship, connecting the bottom plating to the side shell in a joint that would bear enormous stress during ocean crossings and beach landings. Sullivan's modified equipment had been refined during the previous weeks to handle the specific requirements of LST construction. The wire-feeding mechanism provided precise control over deposition rates, while the flux hopper ensured consistent coverage of the arc zone. Most importantly, Sullivan had developed techniques for monitoring weld quality that relied on sound, appearance, and other indirect indicators rather than direct visual observation of the weld pool. The welding process itself was unlike anything the observers had previously witnessed. Instead of the bright arc and shower of sparks characteristic of conventional welding, the submerged arc technique produced a gentle hissing sound and a moving mound of flux that concealed all evidence of the welding operation. The wire fed continuously into the joint, while Sullivan moved the entire assembly along the seam at a steady pace that was approximately 6 times faster than conventional methods. The real drama came during the inspection process that followed completion of the weld. Navy inspectors performed extensive testing, including radiographic examination, which revealed the internal structure of the joint in detail. The results showed complete penetration throughout the entire length of the weld, with no internal defects, inclusions, or other irregularities. The mechanical properties exceeded specifications, and the time required for completion was just under 3 hours, compared to the 18 hours that conventional methods would have required. Hayes immediately authorized procurement of specialized submerged arc welding equipment from Lincoln Electric Company, the leading manufacturer of automatic welding systems. The order included power sources, wire feeders, flux handling equipment, and training materials necessary to implement the process across all LST construction at Seneca. More importantly, Hayes directed that the technique be shared with other cornfield shipyards to maximize the impact on overall LST production. The speed with which submerged arc welding was adopted across the LST program reflected both the urgency of wartime production and the dramatic advantages that the process offered. Within 2 weeks of the successful demonstration at Seneca, Chicago Bridge and Iron had contacted their counterparts at Dravo Corporation, Missouri Valley Bridge and Iron Company, and other LST contractors to share technical details of Sullivan's innovations. The implementation process required extensive modifications to existing equipment and procedures. New fixtures were designed to position hull sections for optimal submerged arc welding. Training programs were established to teach welders the indirect monitoring techniques that the process required. Quality control procedures were revised to accommodate the different inspection requirements for submerged arc welds compared to conventional joints. The most significant challenge was overcoming the psychological resistance of experienced welders who had spent decades relying on visual observation of the weld pool to judge quality. Submerged arc welding required welders to develop entirely new instincts based on sound, flux behavior, and other indirect indicators. The learning curve was steep, but the productivity advantages were so substantial that even partially trained operators could exceed the output of highly skilled conventional welders. The first LST completed entirely using submerged arc welding for major structural seams was LST 600, which was launched at Seneca on May 15, 1943. The ship had required only 280,000 man-hours to complete, a 68% reduction from the 880,000 hours needed for earlier vessels. More importantly, quality inspections revealed that the welded joints were superior to those produced using conventional methods, with fewer defects and better metallurgical properties. The success of LST 600 triggered a cascade of innovations throughout American shipbuilding that extended far beyond LST construction. Liberty ship producers quickly adopted submerged arc welding for cargo vessel construction, reducing production time by 30%. The technique proved equally valuable for warship construction, where the long, straight seams characteristic of naval architecture were ideally suited for automated welding processes. The mathematical impact was staggering. By reducing welding time for major structural seams by approximately 70%, submerged arc welding effectively increased the capacity of existing shipyards without requiring additional facilities, equipment, or workers. The technique enabled American shipyards to produce vessels at rates that exceeded German estimates of maximum Allied capacity by factors that seemed impossible to Axis planners. The psychological impact on workers was equally significant. Sullivan's innovation demonstrated that individual initiative could directly contribute to winning the war, that improvements developed on the factory floor could have strategic consequences. The success of the forbidden technique validated the principle that innovation often came from unexpected sources, that the combination of practical experience and theoretical knowledge could produce breakthroughs that neither could achieve alone. News of the welding breakthrough spread rapidly through the network of defense contractors and government agencies responsible for war production. Sullivan received official recognition from the Navy Bureau of Ships and was invited to demonstrate his techniques at other shipyards. More importantly, his success inspired similar experimentation at facilities across America, leading to additional innovations in welding, assembly, and quality control that collectively transformed American manufacturing capacity. The timing of Sullivan's breakthrough was crucial to Allied strategic planning. The Sicily invasion, scheduled for July 1943, required massive numbers of LSTs to transport tanks and equipment directly onto Italian beaches. The accelerated production, enabled by submerged arc welding, provided the additional landing craft necessary to support operations that might otherwise have been delayed or scaled back due to insufficient amphibious capacity. The transformation of LST production that followed Sullivan's breakthrough exceeded even the most optimistic projections. By May 1943, welding time for each LST at Seneca had been reduced to 280,000 man-hours, representing a 68% improvement over conventional methods. But the time savings were only part of the story. The consistency and reliability of submerged arc welding eliminated many of the quality problems that had plagued earlier production, reducing rework and inspection time by even greater percentages. The first ship welded entirely using submerged arc techniques for major seams was LST 600, completed in just over 2 months from keel laying to launching. The vessel's construction became a case study in efficient shipbuilding, with representatives from other shipyards visiting Seneca to observe the new techniques in operation. The success of LST 600 provided irrefutable evidence that submerged arc welding could produce warships of superior quality in significantly less time than conventional methods. The rapid spread of Sullivan's innovation across all LST construction sites reflected both the desperate urgency of wartime production and the obvious advantages that the technique provided. Dravo Corporation at Neville Island, Pennsylvania, implemented submerged arc welding in April 1943, just 2 weeks after observing the successful demonstration at Seneca. Their first ship using the new technique showed a 40% reduction in construction time, with quality improvements that exceeded Navy specifications. Missouri Valley Bridge and Iron Company in Evansville, Indiana, achieved similar results when they adopted the process in early May. The Evansville facility had been struggling with production targets that seemed impossible to meet using conventional welding methods. Within 1 month of implementing submerged arc welding, they increased monthly production from 4 LSTs to 7, while simultaneously improving weld quality and reducing material waste. Chicago Bridge and Iron's shipyard in Seneca, Illinois, became the testing ground for continuous refinements to the submerged arc welding process. Sullivan worked closely with engineers from Lincoln Electric to develop improved wire feeding systems, more efficient flux handling equipment, and better techniques for quality control. Each improvement was quickly shared with other LST contractors, creating a collaborative development process that accelerated innovation across the entire program. The Jeffersonville Boat and Machine Company in Indiana and American Bridge Company in Pennsylvania both reported similar success when they implemented variations of Sullivan's technique. By summer 1943, all 5 cornfield shipyards were using submerged arc welding for major structural components, with productivity improvements that ranged from 50 to 70% compared to conventional methods. The impact on overall LST production was dramatic and immediate. Monthly production across all American shipyards increased from an average of 60 ships in early 1943 to over 100 ships by year's end. The acceleration came precisely when LSTs were needed most urgently for planned operations in the Mediterranean and preparation for the eventual invasion of France. Without Sullivan's innovation, the Allied invasion schedule would have been delayed by months, potentially changing the entire course of the European war. The Sicily invasion in July 1943 employed 229 LSTs, many of them constructed using Sullivan's welding techniques. The operation, codenamed Husky, represented the largest amphibious assault in history to that point, with Allied forces establishing beachheads across southeastern Sicily, using landing craft that delivered tanks and equipment directly onto hostile shores. The LSTs performed flawlessly, validating both the ship design and the welding methods used in their construction. LST 511, the ship where Sullivan had first perfected his forbidden technique, played a crucial role in the Sicily operation. The vessel delivered 40 Sherman tanks of the 1st Armoured Division directly onto the beaches near Gela, then provided fire support with its anti-aircraft guns during German counterattacks. The ship's performance under combat conditions demonstrated that submerged arc welding produced joints that were not only faster to complete, but actually superior in strength and reliability to conventional welds. The success at Sicily led to even more ambitious applications of LST technology and Sullivan's welding innovations. The Allied landings at Salerno in September 1943 employed over 300 LSTs, including dozens that had been constructed using advanced submerged arc welding techniques developed at Seneca. The operation demonstrated that Allied forces could establish and maintain beachheads on heavily defended coasts, a capability that was essential for the eventual invasion of northern France. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical lessons learned from LST construction using submerged arc welding had implications that extended far beyond military shipbuilding. The process proved equally valuable for Liberty ship production, where the long, straight seams characteristic of cargo vessel design were ideally suited for automated welding techniques. Kaiser Shipbuilding, the largest producer of Liberty ships, implemented variations of Sullivan's methods that reduced construction time for cargo vessels by 30%. The success of submerged arc welding in wartime shipbuilding accelerated development of automated manufacturing techniques that would transform post-war industry. The precision control systems developed for welding, wire feed, and flux application became the foundation for numerical control systems used in machine tools. The quality control methods developed for inspecting submerged arc welds influenced manufacturing standards across multiple industries. The human stories behind the technical achievements revealed the collaborative nature of wartime innovation. Sullivan's initial breakthrough was supported by dozens of workers who contributed ideas, tested modifications, and shared their expertise. Tom Mueller, who had helped develop the improvised equipment used in early experiments, became a training supervisor responsible for teaching submerged arc welding techniques to workers at facilities across the Midwest. Chief Welding Inspector Harold Jenkins created quality control procedures that ensured the new process met Navy standards while maintaining the speed advantages that made it valuable. His inspection protocols became the standard for submerged arc welding applications throughout American industry. Production Superintendent William Hayes provided the institutional support necessary to overcome bureaucratic resistance to change, demonstrating the leadership required to implement innovation under pressure. The women who joined the welding workforce as men left for military service played crucial roles in perfecting and scaling Sullivan's technique. Martha Henderson, a former elementary school teacher from Seneca, became one of the most skilled submerged arc welders at the facility. Her steady hands and meticulous attention to detail made her particularly effective at the precise control required for the process. By 1944, women comprised 40% of the welding workforce at Seneca, many of them achieving productivity rates that exceeded their male predecessors. The success of women in submerged arc welding operations challenged traditional assumptions about industrial work and demonstrated that technical skills could be acquired rapidly when training methods were properly designed. The hidden arc and reduced physical demands of the submerged arc process made it more accessible to workers who lacked the upper body strength required for conventional welding techniques. This accessibility proved crucial as shipyards struggled to maintain production with an increasingly diverse workforce. The collaborative development process that emerged around submerged arc welding became a model for other wartime innovations. Technical improvements developed at one facility were immediately shared with others, creating a network of continuous improvement that accelerated progress across the entire LST program. Engineers from Lincoln Electric worked directly with shipyard welders to solve practical problems, while Navy inspectors provided feedback that helped refine quality control procedures. The mathematical impact of Sullivan's innovation was staggering in its scope and implications. The 200,000 tons of steel welded using submerged arc techniques at Seneca alone represented enough material to build 40 additional LSTs. The time savings enabled completion of the LST program 8 months ahead of original schedules, making available crucial landing craft for operations that might otherwise have been impossible or prohibitively costly. General Eisenhower later credited LST availability as one of the 3 factors that made D-Day possible, alongside radar technology and heavy bomber production. The Supreme Allied Commander's assessment reflected the strategic importance of tactical innovations like Sullivan's welding technique. Without sufficient landing craft, the invasion of Normandy would have been delayed indefinitely, potentially allowing Germany to strengthen Atlantic wall defenses or redeploy forces from other theaters. The long-term consequences of accelerated LST production extended throughout the Pacific theater as well as Europe. General MacArthur's island-hopping strategy in the Southwest Pacific depended on the ability to transport tanks and heavy equipment directly onto beaches that lacked port facilities. The LSTs, constructed using Sullivan's techniques, enabled operations from New Guinea to the Philippines that would have been impossible with conventional landing craft. Admiral Nimitz's Central Pacific offensive similarly relied on LST capabilities for the invasions of Tarawa, Saipan, Iwo Jima, and Okinawa. The ability to deliver tanks and artillery directly onto heavily defended beaches proved decisive in operations where traditional amphibious methods would have resulted in prohibitive casualties. The strategic mobility provided by LSTs fundamentally changed the nature of Pacific warfare, enabling Allied forces to strike anywhere at any time with overwhelming material superiority. The economic implications of Sullivan's innovation extended beyond the immediate costs of ship construction. The ability to produce LSTs rapidly and reliably enabled strategic planning that would have been impossible with slower construction methods. Military operations could be scheduled around delivery dates rather than hoped-for completion times. The reliability of the supply chain allowed commanders to commit resources with confidence that necessary equipment would be available when needed. The technological legacy of submerged arc welding innovations developed during LST construction influenced multiple industries throughout the post-war era. The process became the standard method for heavy shipbuilding, enabling construction of supertankers, container ships, and offshore drilling platforms that would have been impossible using conventional welding techniques. The precision control systems and quality assurance methods developed for wartime production became the foundation for modern automated manufacturing. The international recognition of American shipbuilding capabilities led to extensive technology transfer after the war. British, French, Japanese, and other shipyards adopted submerged arc welding techniques that had been developed in American cornfield shipyards. The methods that Frank Sullivan had experimented with during lunch breaks in Seneca, Illinois, became standard practices in shipyards from Glasgow to Yokohama, demonstrating the global impact of localized innovation. The environmental benefits of more efficient welding were significant even by 1940s standards. Submerged arc welding produced less waste metal, required fewer consumable materials, and generated fewer toxic fumes than traditional methods. The process was inherently safer for workers, with no visible arc to damage eyesight and minimal exposure to welding gases. These advantages made it easier to train the expanded workforce needed for wartime production, including many workers with no previous industrial experience. The personal stories of those who developed and implemented Sullivan's technique reflected the broader transformation of American society during the war. Sullivan himself returned to Chicago after the war, where he established a welding consulting firm that helped introduce submerged arc welding to peacetime industries. His company became instrumental in the post-war boom in construction and manufacturing, applying wartime innovations to civilian applications ranging from skyscraper construction to automobile manufacturing. Mueller became a training supervisor for Lincoln Electric, teaching the techniques he had helped develop to welders across America and eventually around the world. His training programs became the standard for submerged arc welding education, influencing generations of welders who applied the techniques to peacetime construction projects. Jenkins rose to become chief inspector for the entire Chicago Bridge and Iron Company, overseeing quality control for hundreds of major construction projects, including bridges, buildings, and industrial facilities. The cornfield shipyards themselves became symbols of American industrial improvisation and adaptability. The Seneca facility, built on farmland along the Illinois River, launched 157 LSTs between 1942 and 1945. The transformation of agricultural land into a sophisticated shipbuilding facility, then back to agriculture after the war, demonstrated the flexibility of American industry and the willingness of communities to adapt to wartime needs. The last ship launched from Seneca was LST 1152, completed on April 28, 1943, just days before Germany's surrender. The ceremony marking the ship's completion was attended by representatives from the Navy, Chicago Bridge and Iron, and the local community that had supported the facility throughout the war. After the war, the shipyard was dismantled with the same efficiency that had characterized its construction, and the land was returned to agricultural use. Today, only a memorial marker indicates where some of history's most important warships were constructed, using revolutionary welding techniques developed by a Chicago welder who refused to accept that existing methods were adequate for the challenges facing American industry. The marker commemorates not just the ships that were built, but the innovation, collaboration, and determination that made their rapid construction possible. The legacy ships built using Sullivan's technique served with distinction long after the war ended, providing testament to both the durability of their welded construction and the strategic importance of the innovations that made their rapid production possible. LST 511, where Sullivan had first perfected his forbidden technique, participated in 6 major amphibious operations during the war, from the initial Sicily landings through the final assault on Japanese-held islands in the Pacific. The ship's war record illustrated the direct connection between manufacturing innovation and battlefield success. After Sicily and Salerno, LST 511 returned to the United States for modifications that would prepare her for the Normandy invasion. The ship was fitted with additional armor protection and upgraded communications equipment, then loaded with vehicles of the 29th Infantry Division for the cross-channel assault. On June 6, 1944, LST 511 approached Omaha Beach as part of the largest amphibious operation in history. The ship's flat-bottomed design allowed her to navigate the shallow waters off the Normandy coast, while the ballast system enabled her to adjust draft as tidal conditions changed throughout the day. The welded construction that Sullivan had helped perfect proved its worth under the most demanding conditions imaginable, as the ship delivered her cargo under heavy enemy fire. The performance of LSTs during D-Day validated every aspect of their design and construction, from Niedermayer's original concept through Sullivan's welding innovations. The ships demonstrated their ability to operate in conditions that would have destroyed conventional vessels, beaching themselves on hostile shores, withstanding enemy artillery fire, and continuing to function despite damage that would have sunk traditionally constructed ships. LST-511's service continued through the liberation of southern France in August 1944, where the ship participated in Operation Dragoon, the Allied invasion of the French Riviera. The operation demonstrated the strategic flexibility that LSTs provided to Allied commanders, enabling simultaneous operations on multiple fronts that stretched German defensive capabilities beyond their limits. In October 1944, while supporting operations in the English Channel, LST-511 encountered severe weather that tested her construction to the absolute limit. A storm of unprecedented intensity generated waves over 60 feet high and winds exceeding 120 miles per hour. The ship was caught in shallow water near the Isle of Wight when the storm struck, and the combination of massive waves and rocky bottom caused catastrophic structural damage. The storm literally broke LST-511's back, fracturing the main hull girder and threatening to split the ship into two sections. Under normal circumstances, such damage would have resulted in total loss of the vessel and her crew. But the welded construction that Sullivan had helped develop held the ship together long enough for emergency repairs to be attempted. British shipyard workers at Portsmouth performed emergency welding using railroad rails as reinforcing members, creating a temporary repair that allowed LST-511 to be towed to safety. The improvised repair demonstrated both the strength of submerged arc welding and the ingenuity that characterized Allied engineering throughout the war. The ship was subsequently returned to the United States for complete reconstruction, a process that provided valuable data about the long-term performance of welded ship construction. The rebuilt LST-511 was fitted out for a war-bond tour of the Great Lakes and inland waterways, serving as a floating advertisement for American industrial capability. The ship carried soil and palm trees that created a realistic Pacific Island jungle display on the tank deck, allowing civilian audiences to experience something approaching battlefield conditions. The tour raised millions of dollars in war bond sales, while demonstrating the direct connection between home front production and military success. After the war, many LSTs remained in service with various navies, providing decades of reliable operation that validated the construction methods developed during the emergency of wartime production. Several ships saw action in Korea, where their ability to deliver supplies directly to beaches proved as valuable as it had been in World War II. The shallow draft and beaching capability that had been designed for European operations proved equally effective in the complex coastal geography of the Korean peninsula. During the Vietnam War, LSTs provided logistical support for riverine operations, their shallow draft enabling supply missions far inland along rivers and canals that larger ships could not navigate. The versatility of the LST design, combined with the durability of welded construction, enabled these ships to perform missions that had never been envisioned during their original construction. Several World War II-era LSTs remained in active service with various navies into the 1980s, more than 40 years after their construction. The longevity of these ships provided compelling evidence that wartime manufacturing techniques, developed under extreme pressure and implemented by largely inexperienced workers, could produce results that exceeded peacetime standards for durability and reliability. The transformation of LST construction time from 3 weeks to 72 hours represented more than just improved efficiency. It demonstrated the potential for ordinary workers to contribute decisively to technological progress when institutional barriers were lowered. Sullivan's innovation occurred not because he was uniquely gifted, but because circumstances allowed him to experiment with solutions that more rigid peacetime procedures would have prohibited. The technique he developed in the hull of LST-511 became the foundation for an industrial revolution that extended far beyond shipbuilding. The ships constructed using his methods carried Allied forces from the beaches of Sicily to the shores of Normandy, from the islands of the Pacific to the rivers of Southeast Asia. Every successful amphibious operation that relied on direct delivery of tanks and equipment to hostile shores carried within its welded seams the innovation of a Chicago welder who refused to accept that 3 weeks was the fastest America could build the ships that would win the war. In the end, the banned technique became the standard. The forbidden method became doctrine. The lunch break experiment became the foundation for an entire industry. The young welder who crouched in the hull of an unfinished LST, sweating over a modified welding gun that violated every established procedure, became part of the reason why Allied forces could strike any beach at any time, with the certainty that their floating bridges to victory would be waiting when they needed them most. The mathematics of victory were written in many languages during World War II, but perhaps nowhere more clearly than in the welding shops of cornfield shipyards, where reducing construction time from 3 weeks to 72 hours meant the difference between having enough LSTs for D-Day and waiting another year for sufficient forces to attempt the liberation of Europe. The story echoes across the decades as a reminder that innovation thrives when institutional barriers are lowered, when practical experience is valued alongside theoretical knowledge, and when the urgency of great challenges creates space for individuals to contribute solutions that more rigid systems would have rejected. In every LST that carried Allied forces to victory, in every strategic plan that relied on the ability to deliver tanks directly onto enemy beaches, was the echo of Frank Sullivan's forbidden welding gun, transforming industrial desperation into strategic capability, bureaucratic prohibition into technological breakthrough, and wartime crisis into the foundation for lasting change.